Hello everyone. Today I will be showing you how to do question 5 on the FRQ section for the practice quiz on section A3, Kinetics and Equilibrium. So I decided to choose this question because this was the question that I struggled on most, not necessarily because the components of this question were too difficult, but this question does involve some things that we learned in Honors Chem, and I think that maybe I just need like a refresher on this. So not only will I be making this video to help maybe guide some students who are a little confused like I was, but also it's a great way to teach myself how to do this if I were to see this question either on the AP exam or on the upcoming test. So, section A starts off by saying a sample of 100 grams of solid NaHCO3 was placed in a previously evacuated rigid 5-liter container and heated to 160 degrees Celsius. So, I want to start off by saying, usually when we're given liters, so we're given a volume, and we're given a temperature, and we look down, here we can see that we are also given a pressure. These immediately remind me from Honors Chem of our equation, PV equals nRT. Okay, I immediately see all these components of this equation and how I used to go through problems in Honors Chem when we were doing a section or a chapter test on a section that had multiple equations and I wasn't sure which one used for which problems, I would simply ask myself, what is the question providing me with, okay? And whatever it's providing me with would usually then help me to decipher which equation I would need to solve the question. So here I can see that it's giving me a volume right here. I'm going to highlight all of the stuff that it gives me. A volume gives me a temperature in Celsius. It's important that we recognize that it's in Celsius because the T in PV equals nRT always has to be in Kelvin, so we will have to convert that to kelvins. It tells us that some of the original solid remained. This will be important, but actually not for this part of the question. So I'm going to highlight it, but just in a different color. We can do green. And the total pressure gives us in atmospheres. This is also important not only for the actual pressure, but it also tells us what kind of constant we're going to use for R. We know that we will be using the ATM constant, not any other type of constant for a different unit of measurement when it comes to pressure. Okay, so it gives us the temperature right here. It gives us the volume, gives us the pressure, and we already know the constant. So the only thing we're left with to solve is N. And would you look at that? It asks for calculate the number of moles. So P equals pressure, V is volume, N is moles, R is the constant, and T is the temperature in kelvins. So since it is asking for the moles, we know that this was the correct equation that we need to use. It did ask for us to represent that the calculate the number of moles of H2O in present at equilibrium. So here, this is where we kind of start to recognize that we need to start using our balanced chem equation that the question gave us, because we're given two solids in this equation. Now, when we know that when we're given a problem at equilibrium, solids and liquids are not considered. The only thing we consider are compounds that are either in the phases of gas or aqueous. So we will only be using these two compounds, H2O and CO2, for a question like this. So here we can actually start doing our setup for the equation. We have our pressure, which we said was 7.76. I'm just going to put everything in parentheses, so we know to multiply. We have our volume, liters, equals N, which is what we're solving for. Our rate constant, which is 0.0821. How I knew that was a rate constant, like I said, it tells us here atmospheres. If it was something else, it would have been a different rate constant, but because we know that we are measuring our pressure in atmospheres, this is the constant that we will always use for atmospheres. And then we have our temperature in Kelvin. How to do that? We just do 273, plus 160. So when finding the temperature in kelvins, you always get your degrees in Celsius and add it to the number 273. That is 433 kelvins. Great. So now we are trying to find N. So we multiply these two, we multiply these two, and then we will divide whatever this is by this. So actually what we can do is we can rewrite this. How I would rewrite it is 7.76 divided by 0.0821 and 433. There we go. So now when we type that into our calculator, let's see what we get. We have 7.76 times 5. So we have 38.8 over, and then we have 0.0821 times 433, 35.5493. I'm just not going to round just yet. So let's do that. 38.8 divided by 35.5493. So now we get that N is equal to 1.091. I'm just going to go to 3 decimal places after. Or actually, we can just do 3 sig figs, because that's usually the required amount. So 1.09. Great. However, this is where I got stuck. I thought that this was my final answer. When I first went through this question, I was like, okay, perfect. This is my answer. No. Why? This gives us the total amount of moles in the entire reaction at equilibrium. So what am I saying? How do I know that? So these were the components that made up the equilibrium reaction. However, it is only asking for the number of moles of H2O. What did we say affects the equilibrium? Both H2O and CO2. Great. So it's asking for just this, not both of these. This gives us the total amount of moles. So it gives us this moles plus this moles. So the moles of H2O plus the moles of CO2 will equal 1.09 moles. Okay? Now, how do we know how much of this total amount is H2O and how much of it is CO2? Well, when we look at the balanced chemical equation, I hope that we can recognize that there's a coefficient of 1 here and a coefficient of 1 here. So they are equal parts. They make up the same amount, or the same amount of, like, they make up the equal parts of 1.09. So all we have to do, divide by 2. So we have 1.09 divided by 2. Then you have moles of H2O are equal to 0.545 moles. This will be our answer for part A. Great. So I'm going to copy this, Control C, and put it in as our answer. And I will move all of this. And we can move on to part B. So, part B asks, how many grams of the original solid remain in the container under the conditions described in A? This is where this kind of starts to become in. We can see that it says in the problem that some of the original solid remains. Okay? So now it's asking how many grams. We started off with 100 grams. Great. We know that we have 0.545 moles of H2O. Here we can begin to look at the coefficient because it is directly asking about the solid. Therefore, it's not necessarily talking about, like, while the conditions in the container are still at equilibrium. Here it's just trying to ask, if it's directly asking about the solid, this is when we can look back at the equation. We see here that for every 1 mole of H2O, we have 2 moles of NaHCO3, which is the solid that is asking about. So if we go here, we know that we have 0.545 0.545 moles of H2O over 1. We use our little stoich steps, multiply that. Ugh, I hate the way this is formatted. So we have our moles over 1, so we multiply it by, we have our mole-to-mole ratio step, or stoich step, or mole step. There's people call it different things. I remembered it as the mole ratio step. We have, for every 1 mole of H2O, we have 2 moles of NaHCO3, so we're going to have 2 over 1, and we can then multiply that, and it's asking for the grams, so we would have to find the molar mass of NaHCO3. I had looked this up prior. You can obviously use your periodic table to figure this out during the test. So the molar mass of NaHCO3 is 84.01, but I think the answer key, 84.0, was used, so that's what we're going to use for this part of the problem. So we have times 84.0 grams. Now, let's see what this all comes out to. So we have 0.545 times 2 times 84. Great. Gave us 91.56. However, this is how much was used. We have a total of 100. So, if this is how much was used, what are we going to do? Just do simple subtraction, 91.56, and we get 8.44 grams. And that will be your answer for part B. So, we can write it over here, 8.44 grams of NaHCO3. This was just some simple stoich. So you see this? I kind of over-explain a little, but it's just some stoichiometry. The step that I wouldn't forget to do is to remember that the number you get isn't actually your answer. You have to subtract it by the total amount that you put in to begin with. So we put in 100 grams of the solid, 91.56 of it was used, grams of it was used, so the remaining amount of grams of the solid is 8.44 grams. So now we can get rid of this and move on to part C. So here, this is where we kind of leave off honors chem for this part, this specific question, and we talk more about what we've learned so far in AP. Write the equilibrium expression for the equilibrium constant Kp and calculate its value for the reaction under the condition in A. Okay, so here's just asking us, make the expression, tell us what Kp is. Great. So, for those who can't remember Kp, I memorized Kc first, and they're the same. So you just find the pressures, and that will get you Kp. So, for this question, really all we need to look at is the pressures, because it says under the conditions in the reaction. So it tells us the conditions and the reactions in the very first part. So, right here. Okay, remember how we said equilibrium. So the only things we're going to look at, if the question has equilibrium, don't look at the solids. So it tells us that it's an equilibrium. All we're going to look at is right here. Now we said there's a 1 right here and a 1 right here. We just don't see them. We don't need to write them because they're just 1s. But we know that these pressures are equal. So if the total pressure, it says the total pressure in the container, which I'm going to highlight this entire thing in a nice blue color. So it says that the total pressure in the container was 7.76 atm. That means that the pressure of H2O and the pressure of CO2 added up together are 7.76. Great. So what that means is that the pressure of H2O alone is 7.76 divided by 2. So let's do that. 7.76 divided by 2, we get 3.88. Oh, tells us force. Would you look at that? There you go, 3.88. However, it needs the entire thing. So, I'm going to make some space right here. K, or K, P. Oh, this is really sad. I hate the way this formats. I don't know how to write. Superscript. It's okay, though. Kp will equal the concentration squared, or the pressure squared. So pretty much it's the pressure of this times the pressure of this to find Kp. Because these are both have a coefficient of 1. So we said that these are equal, so in reality it is just 3.88 times 3.88, or squared. So here we have Kp equals, let's find what that one is. We have 15.05. That is what Kp is, and we will not be including units for this. Let's highlight that. That is our answer for part C. It did also ask for the expression, so we must write Kp equals the equilibrium expression. So we have the partial pressures. So we have P H2O. So sorry for the way this formats. Obviously, it'll be written a little different. And then P CO2. That's the Kp expression. And the actual value of Kp is equal to 15.05. That is our answer. Now, we've made it to the very last part. Obviously, hopefully this question won't take you all 18 minutes that we've been recording so far. I'm going through and I'm explaining things, and I'm going through exactly how I did things. So a question like this, hopefully, ideally, it'll take you about maybe anywhere from, like, I would say maybe 6 minutes. I think 6 minutes for this question would be good. About a little less than 2 minutes for each question. If you know what you're doing, and you know exactly what needs to happen, which equations you're using, how to format the questions, what exactly it's asking for, you don't miss the tiny things, I feel like a question like this would be manageable to get done in about like 5 or 6 minutes. Then the last part says, if 110 grams of solid, NaHCO3, had been placed in the 5-liter container and heated to 160 degrees Celsius, what would the total pressure have been at equilibrium? Explain. This you need to be very, very focused on. We are actually not doing any equations. We're not doing anything. It tells us that 110 grams of solid Na. So pretty much we're just changing one of the variables here. Instead of having 100 grams of solid NaHCO3, we have 110. We added 10 grams. So it's pretty much saying, when we add those 10 grams, what's going to change? Everything else remains constant. We still have our same 5-liter. Right here, 5 liters. Right here, 5 liters. We still have our 160 degrees Celsius. It's asking, how would the pressure be affected, okay, if we change the grams? So here is where this part becomes very, 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 very important. I'm going to highlight this in a different color. Again, I like purple. Let's do purple. Actually, it kind of makes it hard to see. Let's do orange. There you go, orange. So it says some of the original solid remained just by using 100 grams. Okay? And it gave us this pressure. Well, when we add another 10 grams, we can imagine that some solid will also remain. If we only used 100 and some remained, using more grams of the solid in the equilibrium equation will also have some of the grams of the solid also remaining. So regardless, there will be solid remaining. Whether we add 110 or 100 or 120, there's always going to be some that's remaining. So if there is some that are remaining, there's excess grams of the solid, then surprise, surprise, the pressure isn't going to change, because the amount of grams of the solid, since there's always going to be like an excess, the pressure actually will not change. So since some of the solid will remain when we use the 100 gram sample, without any like temperature changing or anything, then using 110 grams won't affect the equilibrium because it causes the same thing to happen. Solid remain here, solid will remain here, so the equilibrium will not be affected. Therefore, if the equilibrium will not be affected, the atmosphere will not change. So the answer for this is 7.76 ATM. This one was a little bit tricky. This one I was like, wait, what's going on? I didn't understand when I first read it. But then, I went through the answer key, got some explanation done. Pretty much, solid is here. We add more grams, so solid will remain. Equilibrium has not changed. Equilibrium hasn't changed. Other components haven't changed. Temperature has stayed the same. The temperature did not change. The solid, there's some left over here, some left over here. Not going to affect the equilibrium. Since nothing is affecting the equilibrium, the atmospheric pressure will also stay the same. So this is how you complete question number 5 on the FRQ section of the practice quiz for Kinetics and Equilibrium. Good luck with your tests and happy studying. I hope this helped.